Hello everyone, this is another ABAQUS tutorial. In this tutorial, I'm going to show you how to model reinforcement concrete beam column joints and how to perform pushover analysis. In the second tutorial of this part, we will conduct a cyclic loading of these beam column joints. So the structure properties is 1 meter length of the column and 1 meter length of the beam, and we have the cross section for the column is 200 by 200 and 4 rebar 10 millimeter diameter is arranged to the corner and using strap 6 millimeters. So the same rebar for the beam, but the depth is same and the length is 100, so half. Now we go to model in ABAQUS. The material we're using is concrete 25 and steel Q235. Here is the program, and we go to quickly draw column. Using solid elements, and we can give about 2000 extrusion, and I'm going to, this is 200, so I'm going to minus 100 by minus 100, and the positive one is positive 100. This is the column, and the length is giving 1000 millimeter. The second part is beam, the same method, and this time the minus 50, which is the weight of the beam, and minus 100, which is the height, and the second is going to be positive 50, 100. This is the column, and the same technique, the length 1 meter. Now the second part is we want to define the rebars. First, I'm going to define the straps. The straps, I should say, column straps using wire planer and giving this data, and let's see here the cover letter or the clear cover is 20 millimeters, so then it will become 160 by 160. Now taking the rectangle and giving minus 18 and positive 80, positive 80. So this is the strap for column, and we can go to one more called beam straps. The same method, we can check it again, and this is 10 millimeter 18 by 180, and this is it. And now we can go to select this one and give minus 40 minus, and this is 290, and again 40, positive 19. So this is the strap for beam. Now we should draw the beam length rebar or longitudinal rebar. So this is the rebar we want. I'm going to dimension this one from here to here. So this is 1170 millimeter, and this is for rebar 4, and this is for the column. So I can take 1 centimeter or 10 millimeter, 980. It is 950, so 980 is okay. Call column rebar using wire element planner, and I'm going to give 0 0 and 980. So I'm going to back again to code beam rebar, and the beam rebar is 0 0 0 and 170. Also I can consider 118, which is 10 millimeter from both sides, reducing 10 millimeter on one side, 10 millimeter one side, totally 20 millimeter. So this is 2. Now we finished defining the materials, and I'm going to define the properties, material properties here. I want to define the concrete 24. It is in my library, concrete 24. This is CDP concrete 24, and I want to use steel Q345. You can here. Here is steel 235, and now we can see the inside material. So we will conduct a dynamic analysis. We need to define density as well. So density, elastic modulus, and plastic. These 3 properties. And for the concrete, here is the density, elastic, concrete damage parameters, compressive behaviors maximum 25, and the tensile behavior, and also tension damage, and other behavior. And now we want to define some section called concrete, because beam column is same material. I'm going to define one section called concrete. And the second is we have 2 kind of rebar. One is 10 millimeter, one is 8 millimeter. So the 10 millimeter is called rebar 10. We're using beam and truss element, so using this material, and it is become 88 fine 35 like this. So we were going to use calculator. Pi times d squared. So d squared is 100 times 3.15, and equal is become divided by 4. So this is the number 85 for the 10 millimeter. And we want to define one for called stirrups, and this straps is 6 millimeters, so we can get 28.3. If I calculate this one, calculator, and 36 times 0.13 divided by 4, 2830 or 2820. Material. Now we define the material. I'm going to assign them. This is the rebar and beam. I think beam is concrete, and beam rebar, beam straps, and column straps, and finally rebar. Now we create it and we assign materials. We go to assembly, and first of all let me bring the column, and this is the column. Apply, and we want to take the column straps. So now I can use this function, and you can see it's in the center, but we want to take that rebar. Let me temporarily delete this column, select this one, and I want to push it 10 millimeter in the z direction. So start point is 0, and again 0, 0, and 10 millimeter. So we put it a little forward, and you can go to C, and it's inside. If I go, okay, now next I wanna bring the column rebar, and this is column rebar here, and I'm going to rotate using this axis, and I'm going to pick this rebar, that point to that point. So now let's click, and one more thing, I wanna take that rebar, take this one and populate, and this is about 160. So we created another 4, and I wanna take this one again, but I want to bring it a little further because the longitudinal rebar it's not correct, and I'm going to bring it a little further. So 0, and then I can take it 0, 0, and 0, and this is with 10. Now it's better and correct. So next I want to populate this one, and taking this direction, I'm going to bring it forward, and this is off, and we can use 120 or 120. Populate. So this is the column, and it's correct to here. Okay. So now we finished one part. So now next is I'm going to remove and select all of them. Okay. And now this is part, I'm going to remove all of them, and then I want to bring the beam. This is beam, and this is beam. Apply, and the beam straps. Okay, and we can see the location is correct, but we want to make it a little, bring it further. So we can go to here, and selecting this one, I go to undo, and going here and just beam, remove it, and I want to take this one first, 10 millimeter, and putting 0, 0, and then going to 0, 0, 10 millimeter, and it's it. And next I wanna go to bring the beam rebar, and I wanna rotate across this axis, and I want to take it here, take this point and bring it to this area. I'm going to populate the rebar in the 4 direction. The height is 100 foot 180, 180, 180. Now you can see here, and this is also 80. And now we can just select here exactly. Okay. So one more thing, I will take this again, and this time putting 0 and 0, 0 and 10 millimeter. So this is correct, and I want to populate this across the structure. This is also 120. Select this one and exit. So remove these parts. Going to be, so this is okay, and even I can make it 10 and 10 to this is 100, and we want to move. If I go to add all, no need. So this is 2 is out. I'm going to take them 2 out like this. Now it's okay, and we created this area, and now what we're gonna do is to bring the column at the beam, and I want to rotate, selecting all, and rotating this using this direction. So it's a little not in the right side, but I'm going to add everything at all. I'm going back here and making a little changes. So I'm going to putting this to there, and now I can bring this as well. So I want to rotate this, selecting this one and this one here, and I'm gonna take this, select all, and I want to put this to 0, 0. Here is, so now I want to take this one and rotate one more times, and that should be going to be 180. So it's correct now. So now before I put in the right position, I want to go to the part and take the column, create some partition. So I use this method. It is called this one, create dotted plane from offset. So I'm going to click this one, and I want to define the location of the columns. So if I go to here, and I can select this point 400, and this also 400. So what I want to do is going to enter value, and it's going to flip that side. Okay, and it's be 400. So one in another one, going to select this one, okay, and this time going to 600, which is cost 200 the height of the column beam. So now in this direction here, okay, and the depth of the column is 200, so it's be 50 one side, 50 one side. I'm going to again this one, and this is 150. So 50, 100 the depth of column, 150. So here, now I want to create some partition using this one. So selecting this column and selecting this one, and selecting these three, and this one. Now we created some partition that's very important, and we can see here if I want to do not see this, I can go to the view and view, and it is called assembly. Here is called data, and I'm going to shoot up the block. So now you can see there is hiding. So what I want to do is I want to rotate this one again, to select all, and into here select 100, and once I want to bring it in the center to 0 0, and now this is completed, and I want to take this, I can take this point and bring to this point, and now it's totally correct in the right position. And if I go to here, you can see the rebar configuration and everything is properly right. So I can also go to view and show some rendering, list the beam rendering, and you can see how it looks like. And I can go to use section, and you can, if I go to change the longitudinal rebar to some what, and here it is. So we finished in this area, and we can go to the step. We can connect cyclic dynamic, which we use quasi-statics or cyclic application. I'm going to use implicit, implicit. So I want to give about the load or displacement in this location about 20 millimeter. The 20 millimeter should apply during 10 seconds. I want to activate nonlinear geometry and using quasi-static, which is 50-50, 50 dynamic, 50, and I can put a very large number to get the result, and here is 0.5 and going to 1e minus 15, and now it's okay. And we can create some one more thing, the loading for the steel structure we can apply in this part, but for the concrete column it's not correct. We should create a partition in this region, and we should define about this location. So what I want to do is I want to go to part and selecting the beam. I want to create one partition in this region. I'm going to select this one, and let's select this one and flip, and I'm going to give 50 millimeter. Okay, I'm going to 50 millimeter. So this is a small area, and I'm going to partition this one. If I go back to assembly to see how is it, it's here, but I can go back part, and I can delete this one and delete this, and I can go to redefine again, and this time to flip, and I'm going to use 950, so which is going to here, and I'm going to back to this one, and it's going to create, going to assembly, and we created this location. So you will apply load in this area. Now uh, uh, next we go to the step and we can create some point. Let's go to create a point in this two center, and let's create one point in this two center. Because our work is not considering in the top and bottom of this structure, but instead we were focusing on this beam column joint. So for this purpose, we will consider a diaphragm in the top of this, or a stiffener in this area. We're not focusing to see the behavior in this area as well as in the bottom, and one also in this area too. So this is it, and we want to create some reference point, and this is the first reference point for loading point, and this is the second for the considering this other side is quite stiff. We are not going to deform these parts. In the practical, we will let me, here is the paper. I can show you. Here is the paper, and on both side for the loading we have some support. That means that they will not actually will not deform, but instead the deformation concentrating in this joint. So we will focus on this area. So we will add some diaphragm in this two other area. Now what we're gonna do is I'm going to create defining some extra output. Let's taking the failure damage, and I can see the scalar stiffness degradation, and also some other deformation. And the last one is going to create data output, especially the reaction force and displacement in this point. So I'm going to create a set, and I can call it loading point. So that loading point is this reference point, and here I don't want to get as any energy, so I'm going to select the set and this one, and I'm going to give everyone increment. So that's all okay. Missing value. We have to define the U2 in this direction and REF2 and this one. And now we almost here finished, and we go to the interaction. So in the interaction we should create a embedded region for the reinforcement and concrete. I can go to here, select column and this to beam, to remove it, and I'm going to create an embedded region called embedded region, and I'm going to select all this region called select region. So I'm going to import all, and I'm going to select column B. Now I'm going to select this. So now we define an embedded region for the entire structure, and the next is I want to define a contact between this concrete and beam column. So the contact is, I can go to determine here automatically. I can go to find, and it's one contact, you can see here, but that's not proper because it's contacting with a large area. So but I'm gonna using this method. So I can go to contact, not surface to surface, but instead I want to use tie. I want to select node region, and here I'm going to first so I'm going to taking the column, so replace, selecting this surface, and again I'm going to add another node region. I'm going to add everything, and I'm going to select beam, replace. So and now selecting this area, so we created the surface to surface contact with a tie method, which is there is no deform movement, which is quite practical. Now we finished, and now we want to define some multi-constraint point or tie or coupling. So it's up to you that the behavior is same. If you go to use tie, coupling, multi-constraint point, it's okay. It's not too much difference. You can use it. I will use multi-constraint point, and ask me this one. I'm going to select this surface, this surface, this surface. So this is it, and I create a this point and one in this point. I forgot to define a first. Let me define a reference point here, and now it's done, and I'm going to create and selecting this one and selecting this area. Now the next one is this one. Create one other multi-constraint point here, and selecting this surface. So for this one I can use coupling, so there is not any problem. I can say coupling this point as coupling, and ask me to take the point, select a control point, and this is the control point, and I'm going to use node region. Now here is so we finish interaction step, everything. So we want to go to the loading. In the loading, I want to consider this side is totally fixed, and I can go to here in the static called fixed, symmetric, fixed. And I can call fixing caster. So the last one is we're gonna go to the displacement using the dynamic and using this one and selecting this point. So what we're gonna do is I'm going to give a minus 20 during 5 seconds. Without don't need in this amplitude, you also can amplitude, but in the next tutorial we will considering the cyclic, so we will define a amplitude too. So now it's okay, we finished, and we go to meshing. Into mesh, and here is meshing, and I want to give a mesh list 50 is maybe quite large. Beam rebar is 50 is okay, and remember to define element because it's now using beam, so this is actually truss straps, and as it is I'm going to give and define the elements here, and straps is go to 18, the same. using truss, and column using this was 50 with the beam, going to add it, and column straps and column rebar 100. Truss. Now we finished the meshing, and we can see the meshing is completed, and I'm going to create a job, and I can call it RC beam column joint. Submit it. Called the following points in stone cannot mesh beam straps. Yeah, we go to mesh. We forgot to beam straps. Yeah, it's not meshed. Using 18. Okay, and yes, and we want to define the element. So truss. Now we're gonna go to submit. Now it's started running, and we can go. Here is some error. It's called the 3 nodes or missing degree of freedom. The multi-constraint point equation cannot be formed. So that if I go to here, and I'm going to result, and I can go to here to see that warning. That was node. So this is the warning node, and that 3 node point didn't create multi-constraint point. So I can go to just in the beam, and we want to create this area is, so I'm going to use this one, and here selecting this, and I'm going to flip, and I'm going to give it 5 millimeter. It's very less, so 5 millimeter. I'm going to use this one, and so we have created this one. Now we will consider the boundary condition here and the multi-constraint point here. I'm going to column, so the column is also the same. And now we can create. We can go to select this one, and I'm going to select this flip, and it's being about 5 millimeter. So we created this one. So I'm going to select this one and select the entire, and ask me to the mesh will delete. Yes. So we created this one. If I go to back to the assembly, so this is here, okay, and that one is also in the right place. And I go to interaction, and again I can define that 3 multi-constraint point. Selecting this point, and selecting this point and this point, and this is we have selected, and this is the control point. So we do not consider that little area. And next, this is not the correct area. I'm going to define a multi-constraint point should be here, and going to reference point, and reference point going to give this one reference point, and going to interaction and creating multi-constraint point, and this is my control point that is here. So now we release that area which not be coinciding with the boundary condition. So the same for this part as well. Going to back to multi-constraint point and selecting this one and selecting this area. So we are done, and there will not error, but we should go to back to mesh and define mesh for the elements. So I'm going to using 50 and going to be here. So and next we go to beam and defining 50 and mesh it. Now we can go to the job. So now this one, let me check it. Monitor. So in the analysis is almost completed, and I'm going to now resubmit it again. In the previous was without considering these things, so we now we fix that one using this method. We got again this error. So the error because we didn't change the boundary condition of displacement in that area. So I'm going to back here in the displacement parts, and we can see that displacement is coupled with this area. So what I want to do is I'm going to back to the interaction here. One was used coupling, so this coupling is this here. I should remove these parts. So I'm going to pick the surface and I'm going to deselect. Just I want to select again node region and selecting this area, not these parts. So that's 100% the error will be fixed. So I'm going back to here and going to submit it. Now it's running and we can see this is the running status. So it takes some while to finish, and I will post the video, and after that we will see the result. Now the analysis stopped because it has made too many attempts made for this. Sometimes this caused because a lot of deformation is occurred, cracks, some end deformation is happened. So we can go to see just the result. If the result is acceptable, if there is deterioration, and we can say yes, otherwise there is no. Now we can see the steel is reached to the ultimate strain, so obviously there is a loss of damage in the concrete. What we're gonna do is I'm gonna go to here and just call parts, and I'm going to take the beam and column. I'm going to replace, and you can see here is about 7 megapascal. And let me do animation, and you can see the things we're giving is that multi-constraint point, which cause to consider the stress and damage in this total area. Now what we're gonna do is I wanna show the concrete damage. So still the compressive damages didn't reach, but in tension, so mostly this area is tension, so here is the significant tension is happened even when it means the tension is reached. So that's just two elements is left, so other is totally collapsed or failed. In case if I consider a dynamic analysis and define some concrete failure, and then this element should remove, so there is nothing to left, and obviously we will get a curve with deterioration in the output, and we want to define this, see these two data. So now here is the result. So the result is very nice, and I'm going to create the operate, and I'm going to create combine, and that should be -1 times because it's in negative, and going to comma, and again -1 times or F2. So I'm going to save called false displacement curve. And now it's okay, and we can go to just plot this one. So this is the behavior. It's a very nice result, which costs about 10 kilonewton to deform. So we didn't define some degradation, some failure, so we didn't reach to more, but we have something that we can get a better result than that one. So we should define a fine mesh. This mesh is not correct because it's very coarse mesh. When it's a large mesh, so then we will some element this they very well deform. So and then loss of large area will deform, because as much as we make a fine mesh, the result is will be better. If I go back and change the column, the beam mesh size, and you obviously see a little difference result. So if I continue to change a lot, so the video will become more longer. So here is the end of tutorial. If you have any question, please put in the comment and we'll find time to answer you. See you next time.